Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Welcome to our webinar on automated security testing throughout the automotive lifecycle.
My name is Christoph Schmittner and I work as a researcher on safety and security co-engineering at the AIT, Austrian Institute of Technology. Here I focus on model-based approaches for security analysis, security design, and security testing. I'm involved in the standardization and was here active in the development of the ISO SAE 21434, ISO PAS 5112, and ISO 24089, and I'm also actively involved in the subsequently developed standards.
And now I'll introduce myself a little. My name is Stefan, and I'm a technology scout with AVL's Advanced Software Solutions department, which means that we are more in the product branch of AVL. And within that role, I'm responsible for research in cybersecurity, which means liaison of cybersecurity partnerships, setting up funded research projects and stuff like that, with the ultimate goal of pouring in knowledge from academia into AVL's product. Before that, I was in an RTO, which means that I come really from cybersecurity research. I didn't have an automotive background before joining AVL. This is something I got only during my work here. So without further ado, let's get on with the topic.
When we talk about cybersecurity testing, then we refer here to the cybersecurity testing, which validates the functionality of our cybersecurity design and which provides documented evidence of the working of cybersecurity design. And cybersecurity design is based on risk analysis. We identify risks, we evaluate which risks we can accept and which risks we want to mitigate. We plan security controls that mitigate these risks, and then we test the security design to demonstrate that our risk mitigation, our security controls are efficient. If we look at the life cycle of a vehicle, then obviously during the planning we have the analysis of threats, the TARA, which relates then later on, if we have the vehicle produced, to the security test, to the final demonstration of security. But analysis of risks, of threats, of vulnerabilities, and testing of security controls is also a continuous activity which we have to continue during the usage phase, since new vulnerabilities can be detected at any point in time, and we then have to decide if this is something we have to address. So if we have to implement new, improved security controls, or if this is something which is still okay, our security design is still efficient enough. The automotive ecosystem makes this automotive cybersecurity testing quite challenging. Modern vehicles have various entry points for potential cyber attacks, wireless interfaces, infotainment system, onboard diagnostic, which all require different approaches, techniques, tools, methods for testing. Inside the vehicle, there are legacy systems which might be difficult to enhance security and where we rely on defense in depth approaches. We have the scale of electronic control units in vehicles. Beside the scale of electronic control units, also the number of interconnections and communications between them. And then we also have to consider that we are in a safety critical environment, meaning for this testing, we have to bring the vehicle in a situation, in a place where we can test the security without compromising vehicle safety. And then we also have to be aware that if we have software updates, we are in a time-sensitive situation, meaning the time for testing the security and the effort we can spend is restricted. And we also have to be aware of the regulatory compliance and the need to have the cybersecurity testing as a sort of continuous activity which integrates into our other cybersecurity monitoring activities. If you do this manually, this is time consuming, this is complex, the repeatability is challenging. It depends to a very high degree of the expertise of the tester, and we have difficulties to have this clear traceability from the analysis, from the vulnerability we plan to address to our test activities and test results. And therefore, we see here room for improvement to go from this manual cybersecurity testing to a more interconnected approach, which connects from analysis to testing in a better way. If you talk about security analysis and linkage to testing, security analysis takes the system, the function, the vehicle, and on the one side tries to identify potential impacts. This means we're looking at the damage scenarios, we're looking at the assets, and try to identify what damage, what impact could be caused, and this then leads us to certain security goals. On the other side, we are aware of the attack surfaces, we are aware of the interconnectivity, and we try to identify, based on risk catalogs, threat analysis, attack path analysis, the likelihood of attacks, which then leads us to certain security controls in order to build barriers, hindrances in this attack path. And if we want to test this, then we have to be aware on the one side that we can tailor our security testing regarding the rigor. That means the effort we spend on testing, the test duration, how many test cases, which expertise and personnel we use, but also on the methods we are using for testing, meaning do we go to penetration testing, do we have a vulnerability assessment, fast testing, which all require different tools, expertise, and offer different level of results. And this tailoring is quite challenging because it then also goes into the argumentation if our security testing really demonstrates that our security concept is working. From the analysis point of view, in order to make the whole approach repeatable and in order to be aware and capable of reacting to design changes, to software update, the best thing is to have here a cybersecurity system model. That means take the vehicle and model the cybersecurity relevant architecture, component, properties, and allow here an automated analysis. That means we take this architecture, we take this model, we have a catalog of threats. We identify, based on this catalog, which vulnerabilities, threats are relevant for our system, and then we have a combination of threats in order to come to attack paths. If we look here on a system model, if we look here on a existing example from research, then one potential attack could be that there's a remote connectivity to an external systems. There is an infotainment system which has an old Bluetooth, an old wireless interface with vulnerabilities, and an attacker would be able to utilize these vulnerabilities in order to gain entry, in order to attack here then the inner parts of the vehicle. And if we have here an automated approach, if we have here this model-based approach, benefits is also that we have here a repeatability and an iterative approach. Meaning if we have a new security design, if we have new security controls, if we update our system, the whole security analysis can be repeated quite fast. And this allows us to derive here the relevant attack paths and the security controls. We plan to restrict this attack path in a very efficient way. But still there's the issue, if we have our security controls, if we have our attack paths, we know what we want to test. We know that we want to test the working of the security controls, but regarding the methods and regarding the effort, the rigor to spend, there is still a question how to define this. And there are two concepts which go in this direction, which works on the definition of how to tailor, based on our security analysis, the testing efforts. And obviously what we would like to do is to say, okay, we decided on the risk treatment. We want to reduce the risk. We have our cybersecurity goal. And now what is the level of reduction and what do we need to do to verify the whole reduction? The first thing, which is already included as an informative annex in the 21434, is the cybersecurity assurance levels. There's currently work ongoing to refine and extend this guidance. And the idea is that the cybersecurity assurance levels give us guidance on how much effort we spend, how much rigor we spend during design, during development on verifying that our cybersecurity is working. So really the assurance, yes, the security control is working. And obviously, since this is guiding the whole lifecycle, the whole development, it would be ideal to have here a very stable parameter. So to have here something which is not changing, and this is then one of the reasons why it's not advised to use here the risk, but more to go on the functionality of an item or on the impact. So use parameters which are relatively stable during the development. And this allows us to define the effort, the rigor we want to spend on testing. We still have the open point, how strong should our security control be? And there's now a new terminology, a new approach, which is a target attack visibility. This is not yet contained in 21434. This is a novel concept. And this target attack visibility is a measure for the expected strength of a selected security control. So the difference if we go to a symmetric or to a asymmetric encryption. And since we define here the estimated or the targeted risk reduction, one of the parameters which can be taken into account is the initial likelihood of a certain attack path. So where the cybersecurity assurance level is more aimed at the impact, at this high-level parameters of the damage scenario, the target attack visibility can be more specialized, really different for different security controls, for different security requirements, and be different depending on which attack path, which security control we are considering. And it indicates the strength of security control, the expected resistance. And if we now want to connect from the analysis where we define our TAF and CAL to testing, we have for TAF the strength of security control, and that means with this information, we can tailor the tools and techniques in testing. We can tailor which security testing approaches are we using. Is this something which we expect it only resists an unmotivated drive-by attack, or is this a security control where we really say, okay, good, a motivated attacker should be stopped? And for CAL, we are looking at the other parameter. We're looking at the rigor, the effort, the time spent on testing. So is this something where we say, okay, good, we have one test case and this one test case worked and now we are happy? Or is this something where we really have to define a consistent set of test cases which tests all potential parameters, implication of an attack, and is then a very detailed answer on the question, how much assurance is our testing giving?
So how can we use all of this to plan our verification and validation through testing? Well, the concept of our overall system testing stems from the theory we have just done before. From the goals and requirements, from there comes our V&V planning. Dependent on the goals and requirement, we choose verification and validation methods. This can include fuzz testing or integration testing, but also model checking of behavioral system models. And there, our flavor of model-based testing comes in. We derive single component models through learning techniques and validate them. Once we've gained those models, we can use model checking to see if there is some violation of the specification or some security problem in there. Through the results of the model checking and also with the use of the traces gathered through the learning process, we can automatically generate a test case. Besides, we are using also generalized description of specific attack vectors that we can later on tailor to specific systems and the test. I will explain this a bit more in a few slides. We reach a great degree of automation by running those tailored attacks and also the test cases from the model-based testing on an automated V&V execution platform. In order to understand how we come from a terror to a test case, we have first to explain our mechanism of generic test cases, which we use to have generalized recipes so that we can reuse tests on different systems. This is crucial for automation, of course, because as all of you know, the systems in the automotive domain are pretty heterogeneous, proprietary, and therefore reusability is pretty low per se. To cope with that problem, we try an approach of generalization to port attacks. So in principle, we use a test case, which you can see in the graph here on the right side in blue, sequence it into atomic parts, which we call test scripts. These are the single steps of a test case to be taken to basically attack a system. And then out of each of these scripts, we basically strip any information that's specific to a system and a test. Out comes a test pattern, which you can see in dark green on the left side. And when we put those patterns together, we get a test scenario. The difference between a test scenario and a test case is that the test case is a functional thing that you can actually run to attack a certain system and a test. And a test scenario is not runnable because we have basically ripped out information that's probably needed to run the test case. But on the other hand, as the positive side, this test scenario is generic, so it's basically fit for any system. And when we actually want to test a system, to use this recipe on a certain system and the test, we then have to concretize it again. This is like filling the gaps we tiered into the test scenario before by generalizing it. So if you have an attack running on a certain car A, we generalize it, and later on when we want to test car B, we just have to fill in the gaps through information either out of our own test databases, or if we don't have them, through information from the OEM or supplier or whoever the customer is. And for these test scenarios, we have developed our own attack description domain-specific language. I'll give an example later on. And these scripts in our attack description DSL are the target of the transition from the attack tree. So now I want to give you a more tangible example how this abstraction and concretization runs based on a real-world example. Here we have a quite simple two-step scenario. First, we want to access an infotainment unit, and from that infotainment unit, we want to send a CAN message that actually manipulates the speed gauge. So for the first part is exploiting the Bluetooth interface of the infotainment unit. On the left side here, you can see how this is built up in our domain-specific language. First, we scan for a Bluetooth interface, then we try to exploit it via Blueborn vulnerability. Then, in this case, we want to open up a rogue Wi-Fi hotspot where the infotainment unit connects to. And through that Wi-Fi hotspot, through a vulnerability, we are able to exploit an Android debug shell on the system. This is sketched in the test scenario on the left side. And on our machine, it's later on compiled into basically a JSON format where we can actually give commands that can be executed on a Kali Linux machine. And the same thing happens for the second step. Once we have access to the infotainment system, we install our environment that we would need to send CAN messages. And in that case, we send a CAN message to manipulate the speed gauge. In this case, it was an older Mazda model, so we didn't have to overcome a security gateway or stuff like that. But in principle, any further step would actually happen the same way. It will be just building blocks in our testing scenario, and once we are on the system on the test, we make it concrete by filling in the blanks. Basically, we left out by abstracting the attack from another system and then trying it out on the target hardware, basically. The tricky thing is now, of course, to get from a Tera to actual test cases. We want to try an automatic approach so that we don't have to do too much engineering to come to our test cases. To do so, we have chosen to take the detour via an attack tree. Out of the system model and the underlying threat generation rules, we cannot just evaluate single components, but also can generate complete paths for attacking a system, meaning taking a specific potential entry point and a potential target, we can calculate and evaluate a path that leads towards a successful attack. Combining all of those paths together, we can generate an attack tree of the complete system. As the underlying information form of the system model and also of the threat generation rules are very formalized, we can generate these paths and the attack tree completely automatically. And once we have our attack tree, we can apply a transition mechanism to semi-automatically try to map the attack tree into elements of our attack description domain-specific language. This language is what I've talked about before, the generic attack descriptions for specific attacks on systems that we later on could tailor towards actual implementation of systems. So having two formalized systems, one is our domain-specific language called ALIA, agnostic language for the implementation of attacks, that we can use to describe the recipes for attacking an automotive system. And on the other hand, the attack tree that stems from our Terra, we can use an automated translation mechanism to actually translate one into the other. As we want to use the results of the Terra to form test cases, the natural translation direction, of course, goes from the attack tree to the DSL. To explain the transition or translation mechanism in very short, we use the notion that everything we use to traverse through the attack tree corresponds to actions. So in principle, any edge in the attack tree where I get from one node to another is basically an action. And this action, of course, could correspond to an action described in our domain-specific language. Therefore, the edges of the attack tree will be tied to lines into our domain-specific attack language. Of course, there are special cases like conjunctions, conditionals, and so on. And frankly, this is ongoing work to make both the attack tree description and our domain-specific language mighty enough to actually allow for such a translation mechanism. Another method of generating test cases inside our system is model-based testing. We try to infer a behavior model of our system on the test through learning techniques. We therefore have created learners for different protocols that are proliferated in the automotive world, like Bluetooth, Wi-Fi, but also the Unified Diagnostic Service, UDS. And we are capable of learning behavior models of those systems. And with those models, we can apply rule sets on for model checking. And therefore, we can check if these systems we have in front of us are conform to a certain specification. And that specification is either just being conformed with the standard or adhere to certain rules that certain conditions must be must hold, or certain conditions are never allowed to happen. And if this is somehow violated, we have a potential security issue there. And once we find such a violation, together with the information from the learning, how we got into that state, then we automatically can form a test case and try it on the real system. And if the real system behaves just like we predicted into our learning model, then we have found a security issue because the model checking applied rules that basically look for potential security problems. If this prediction was incorrect, then we have done something wrong in the learning of the behavioral model, and we have a counterexample so that we can learn a better model. And once we have a good or next to perfect model, we can do the model checking again and see if this model still violates some specifications and therefore has potential security issues. And all of this runs on our automated security testing platform. This platform basically consists of two machines. One is for orchestration, and the second one is a Kali Link's machine that actually executes the tests. The second machine gets the test cases in a JSON format where they have been basically compiled on the first machine from our test script and some additional information you can see here. The test scripts come out of the attack database, and the additional information, as I said before, to fill up the blanks for concretizing the test case comes either from an SUT database, or if we lack of information, then they have to be provided by the customer. The second flavor, as said before, is model-based testing. The inferred model is used by our testing platform to guide fuzz tests or to derive test cases through model checking, just as I said before. I will now show how this process runs in practice. Firstly, we use different projects to tailor our testing process to the respective system and the test. In these projects, we need to link together the system and the test, execution agents, because we can actually utilize more than one execution engine, and of course the test vector, which is the test scenario I was talking before. This therefore contains all the information that's needed to compile an actual test case out of the test scenario and the system and the test information. We therefore need to specify the system and the test and link the test scenarios with the information of the SUT database I was talking about before, or with the customer information. And this happens basically here so that we can actually choose which CAN messages are needed to be sent, for instance, to manipulate the speed gauge, or which exploit we would use to actually try to rip the infotainment system open via Bluetooth, depending on the Android version and other parameters. Then we basically choose how we want to carry out the attack. For instance, we could choose a version of our execution engine running on a PC, which is the standard, or also on a Raspberry Pi for portability, so that we can actually place an execution agent or an execution engine inside the system and the test and perform the test on the test track easily. When choosing the test cases here, we actually choose such a test scenario out of the scenario database. This means basically the recipe for the attack that will be compiled with the SAT information together to actually perform the attack. Here you can see the contents of the test case, and this is actually the description in our domain-specific language, just as you've seen before in our example. So the let's say the instructions to carry out the tests, just like before, scanning for Bluetooth, exploiting, and so on. And this is then actually what's being linked together with the system and the test information to provide a JSON format instruction to carry out the test to that test agent. So then the test run is carried out on the execution engine using the JSON-based instructions it gained from the orchestration, where it's been generated out of the DSL recipe. And so you can track the progress of the test case to be carried out. You can monitor each step and also view the actual instructions in JSON that have been generated out of the DSL and the SCT information. Also, you can monitor the pre and post conditions. The preconditions are set because sometimes it just does not make sense for an attack step to be carried out. For instance, to try to exploit a Bluetooth interface if none can be found. And also the post condition, which are information for the oracle in order to determine if the test was successful or not. That concludes our talk. We want to emphasize that validation and verification through testing is of other importance. And for a holistic concept, we can derive the tests even directly from the Terra. And finally, also, CALs and TAFs help us in finding the right amount of testing. So thanks for watching our webinar. If you have any questions, please feel free to contact us at the emails you see below.